steam distillation. In this video, you will be learning about the liquid-phase equilibrium scientific background of steam distillation. Before we move on to steam distillation, we need to understand the concept behind the normal distillation. We learned in Raoult's law how an ideal solution behaves with its composition. How does the vapor pressure of the solution change with the composition? How does the boiling point of the mixture change with the composition? Let's have a quick review on Raoult's law of a binary solution. Here are the two miscible liquids which are volatile and have their saturated vapor pressures under the same temperature, A P0 A, B P0 B. You remember when these two liquids are mixed, due to the mixing, the number of particles which can evaporate per unit area of the surface is going to decrease for each substance. The vapor pressure produced by each component will be less than their saturated vapor pressures. PA is less than P0 A, PB is less than P0 B. Since we are dealing with ideal solution, we have assumed the intermolecular attractions between A and A, B and B, finally A and B are all the same in the strength. The behavior of this solution is going to depend on the total pressure generated by the vapor, and that is going to depend on the composition of the liquid. So let's apply Dalton's partial pressure law. The total pressure is equal to the addition of the partial pressures. Now let's apply Raoult's law for each partial pressure term. You know that according to the Raoult's law, the partial pressure is equal to the saturated vapor pressure of the liquid and the mole fraction of the particular component in the liquid phase of the solution. So PA is equal to P0 A into XA liquid in the solution. PB is equal to P0 B into XB liquid in the solution. So when we substitute the Raoult's law expressions to the Dalton partial pressure, we get the total pressure is equal to addition of these two terms. The total pressure is not going to be above the saturated vapor pressure of the more volatile component, and it is not below the saturated vapor pressure of the less volatile component, which means it is less volatile than A. The solution's boiling point is always higher than the boiling point of A. It is more volatile than B, therefore its boiling point is always less than the boiling point of B. This is how the pressure of A changes with its mole fraction from 0 to 1. It goes to P0 A. This is how the pressure of B changes with its mole fraction. So we combine these two and get the total pressure variation. Its minimum value is P0 B, its highest value is P0 A, and this is the result. The boiling point of the mixture is always less than B, which has the highest boiling point out of these two liquids, and it is always higher than the boiling point of A, which has the lowest boiling point out of these two liquids. So the solution's boiling point varies in between these two values. So we can understand this very easily from the pressure versus temperature graph. A reaches the external pressure and boils at a lower temperature, whereas B reaches the external pressure at a higher boiling point. Since the solution has its vapor pressure always in between A and B, its boiling point will be in between A and B. That is a summary of a binary solution which contains two miscible liquids, provided that it is an ideal solution. If a mixture of miscible liquids behaves like this, how would a mixture of immiscible liquids behave? That's what we need to understand in the next explanation. Have you seen mixture of water and kerosene, water and coconut oil, water and any essential oil? The behavior of such liquid mixtures is different from the miscible liquid mixtures. So steam distillation is dealing with such immiscible liquid mixtures. Now we'll see the theoretical background of steam distillation, or the behavior of mixtures made of two immiscible liquids. Let's take A and B, which are immiscible liquids. The saturated vapor pressure of A is higher than B, which means its boiling point is less than B. When these liquids are the pure liquids, they have their saturated vapor pressures in the liquid vapor equilibrium. Now we mix these two and form a heterogeneous mixture. When you mix two immiscible liquids, the liquid which has a low density will float on the other liquid. You might misunderstand, therefore the bottom layer will not be able to evaporate. We have to think a little more rationally. What will happen when we mix this mixture thoroughly, or stir this mixture thoroughly? The liquids will break into small droplets of liquids, and both the liquid droplets are able to evaporate because they are coming to the surface at that moment. So this diagram shows you the separated two liquids. They never remain like this, but let's theoretically take these two are not miscible. Therefore the molecules have equal chance of evaporating. Since they are not mixing, the amount of particle of each substance in a unit area on the surface will be unchanged. So both the liquids still have the same ability to evaporate, and there is no vapor pressure depression for each component. But in the miscible ones, due to the presence of both particles on a given unit area of the surface, they have less chance to evaporate, not because of intermolecular attractions, but because of the number of particles available in a unit area. Therefore, there was a vapor pressure depression. But in this case, there is no vapor pressure depression. The gaseous state will still have P naught A, that means the saturated vapor pressure exerted by A. The gaseous state will still have the saturated vapor pressure exerted by B. So if you are going to calculate the total pressure is the parameter which is going to decide the properties of a mixture. So if you look at the total pressure, we can calculate it using Dalton's partial pressure law. So you get P naught A plus P naught B. Unlike the previous case, it was PA plus PB, and PA was substituted by the Raoult's law expression. But here there is no Raoult's law to be applied, because there is no mixing of liquid. There is no mole fraction of a component in the liquid state, since the two different liquids are not mixing. So we have the saturated vapor pressures added up. Therefore, I can definitely say the total pressure will be higher than both the saturated vapor pressures of the two liquids. It is higher than P naught A, obviously then it is higher than P naught B, because P naught A is higher than P naught B. So when the mixture has a greater vapor pressure, which means now the mixture has greater tendency to evaporate. So that will have an effect on the boiling point. What is that effect? The boiling point of the mixture is going to be lower than the boiling points of both the liquids. So it's interesting. The boiling point of the mixture is going to be lower than the one with lower boiling point, that is A, which has a lower boiling point to B. So your mixture is now more volatile than both A and B. That's why when you mix kerosene and water together, the boiling point of the mixture is going to be less than the least boiling point one. So we understood the situation when the two liquids are not miscible, it's only the Dalton's partial pressure law is going to work here, and the total pressure is always greater than the saturated vapor pressure of each component. That means it is going to boil before both the pure liquids. So the summary of what I explained to you is in this graph. You can see how the saturated vapor pressure of B changes with time. Since it is less, it has to be heated more, so its boiling point is higher. Then only it can reach the external pressure. A is more volatile. Its saturated vapor pressure is always higher than B, and it increases with the temperature. It reaches the external pressure at lower temperature, that means its boiling point is less. The vapor pressure of the mixture is always the addition of two saturated vapor pressures. Therefore, it is always greater than these two. As a result, the mixture reaches the external pressure at a lower temperature than the pure liquids. So it boils at a lower temperature than the two liquids. Here is a common example in which steam distillation is carried out. Phenylamine has the normal boiling point of 184 degrees Celsius and water has the normal boiling point of 100 degrees Celsius. And phenylamine is an organic liquid and it is not mixing with water. These two are going to form an immiscible mixture of liquids. We will see what will happen to their saturated vapor pressures. When you heat the mixture at 98 degrees Celsius, the saturated vapor pressure of phenylamine becomes 7.07 kilopascal and water is going to become 94.30 kilopascal. So when you add them up, this will exceed 100 kilopascal, which is the atmospheric pressure, which means the mixture is going to boil. And the mixture is going to boil at 98 degrees Celsius means it has the boiling point less than both of them. So we have been talking about the theoretical concept of this. Let's move on to the practical aspect, or how can we carry out steam distillation and what apparatus to be used in the process.
Water is boiled inside the steam generator and the steam is sent through the delivery tube into the round bottom flask. The safety tube makes sure the pressure is mediated. Now the mixture to be distilled undergoes boiling and the vapor will be then sent through the delivery tube into the condenser. Inside the condenser, the vapor is cooled and condensed. The condensed liquid is collected in the receiving flask. You may see two layers of liquids.
What are the uses or the advantages of doing steam distillation? Most of the liquids that we extract in steam distillation have higher boiling points than water. Not only they have high boiling points, they are thermally sensitive, which means if you heat these liquids to their boiling points, most of the time they will undergo some other reactions. They can get oxidized, they can undergo cracking, or even they can get combusted. But when you do steam distillation, these liquids will boil along with water less than 100 degrees Celsius due to this concept. And the resultant distillate is easy to separate because water and these liquids are not miscible. Using separatory funnel or some other industrial method, you can easily separate them. So in this short video, you learn steam distillation, the theoretical background of steam distillation, the examples of steam distillation, and the uses, finally the practical aspects of steam distillation. Hope you enjoyed. Thank you for watching.